Recording in progress.
All right, so 6.2 and 6.3 today, 7.1 and 7.2 on Thursday. We will do a review on Tuesday next week, and it can take as long or as short as we want. Bring questions if you got them. Thursday, midterm opens at 12:01 a.m., which is Wednesday at midnight. I recommend it. This is on my math lab, and the questions are very, very similar. There is a review exam. We're not going to walk. Well, we could walk through that. There's a review exam on my math lab. And you can take it as many times as you want, and it will change the questions and stuff like that. And yes, once you start the midterm, you have to finish. That's what one of the students asked. You do have to finish. You have, I think it's 2 hours or 2.5 hours. I have to look. You have to finish because otherwise students would scroll through all the questions, look really quickly, write them all down, stop the video or stop the test, go look everything up or get help doing them, and come back and try to finish the test later. That doesn't work. That would, if I enabled that, I'd get a lot of 100% because everybody would be cheating. I can't do that. So you got to do it all at one sitting. The review exam, they have multiple examples or multiple types of questions for the same category. It's worth doing 2 or 3 times if you've got the time, just so you can see all the different types of questions. If you're a go-getter and you write down all your questions and your answers, you might see questions that are very similar on the midterm, down to word for word, but maybe the numbers are different, and you'll have notes for how you did it. That's a lot of work writing it all down. I recommend at least just going through them and seeing the questions. But that's for that test. Let's focus on 6.2 and 6.3 today.
When will our midterm be due? So
It opens up
Oh,
October 6th at midnight. It's due October 11th at midnight. October 6th at 12:01 a.m. October 11th at midnight, which is Tuesday at midnight. Like Tuesday 11:59 p.m. That kind of. Does that make sense? I think
yeah.
it's Tuesday. Now I'm second guessing myself. Let's go down and look at October. October is 11. Yeah. Tuesday night at 11 p.m.
So for that Tuesday, we're gonna have chapter 7 due, the homework, and we're gonna have the midterm due.
Everything's due.
Okay.
It was chapter 7's homework was originally due next week before the midterm started. I extended it to give people more time. So, like if you're doing homework and you're not working on the midterm till like Sunday, you can still work on homework all the way up to the before you take the exam. We don't need that. Where was I? 6.2. 6.2 is on binomial probabilities. Binomial, like bicycle, bi is 2. Binomial probabilities have only 2 outcomes. It could be yes or no. It could be success or failure. It could be, anything like that. There are 4 criteria to using the binomial probability formula. So we have a formula. And it requires the following. We need a fixed number of trials. So like coin flip is a great outcome, heads or tails. We need to use this formula. We need to say we're going to flip the coin 10 times. Okay? We can't say we're going to flip the coin until we get 7 heads. Because that might be in 7 coin flips. That might be in 700 coin flips if you're just unlucky as hell. So we need a fixed number of trials. Like the events have to, Only so many times you're doing it and checking for the event. The trials do need to be independent. Which is quite frequently the case. Coin flipping, there's no reason one coin flip affects the next coin flip. But if you're drawing cards, if you draw a card and leave the card out that you drew, the next card is affected by it. So, like independent trials for cards would be putting the card back in the deck after each time you draw it. C is two mutually exclusive outcomes. And that's what I was saying up here. That's the C idea. They have to be no overlap between them. Yes is yes, no means no. There's no means yes or anything like that. It's either true or false. No, like sometimes it's true, sometimes it's false. And the last thing that has to stay true is the probability has to remain the same between events. And I'll usually describe that as fixed probability. The probability is fixed to be a specific amount and it cannot change. I think I'll give you a second to write that down. I think it's better to look at a couple examples and go, does this meet the binomial probability formula rules? And that way you get a better feel from it from there. If you see me pause and get choked up for a second, the dog behind me in the picture, his name is Astro. We've had him for 8 years, 8.5 years. We got him when he was 8 weeks old. He died inexplicably on Saturday night. Just started having problem breathing, and we couldn't get him to the vet fast enough. He just passed away. So we're pretty torn up about it. We don't have children. We loved him a lot. All right, so I will do my best to focus on classwork, but I just want to let you know if that happens, that's why. Let's look at some examples. So example number one, let's see, Jackie was the one talking to me a little bit ago. Jacqueline and I play rock, paper, scissors. Three times. Let's go 5 times. I record the number of times I win. Does this meet the rule for binomial probabilities? So when I say I record the number of times I win, this is like my random variable. Random variable x. We talked about random variables last week, RV. I usually abbreviate. I'm saying x equals, and what are my possible outcomes? I could win 0, 1, 2, 3, 4, or 5 times. Those are my possible outcomes. So we're not recording what I throw. Doesn't matter if I throw rock, paper, or scissors. The only thing we're caring about is if I beat Jacqueline. And I just totally fucked Jacqueline's name up. Look at that. I got a K in there like a moron. I had the name, I was about to write Jackie with like Jacky. Sorry, Jacqueline. Fuck that up. All right, so does this meet my list up above? A, B, C, and D. Are there a fixed number of trials? I said we were going to play 5 games. So, yes. B. Are the trials independent? Well, they should be. There shouldn't be any pattern between what I throw and what. Some people play they throw something different each time. When I play rock paper scissors, I like randomly select at that moment what I'm picking. Sometimes I'll throw rock like 5 times in a row. Sometimes I'll mix it up. So it's independent. Yes. What I do in one trial, or whether I win one hand, has no connection to whether or not I win the previous hand. Are there 2 mutually exclusive outcomes? Yes. I win and I record one, or I lose. Lose/tie. And finally, D, is the probability same for all events? Yes, I have a 1 in 3 chance of beating her. If I throw rock, she has to throw scissors. There are 2/3 chances of losing or tying, 1/3 for each. So those probabilities remain fixed. They're not equal. They're not equal to each other. But they are the same every round. And that's worth noting. So yes, this counts as a binomial probability event. Is applicable. Ready for another example? I'm going to erase what I have on the screen so I can keep those probability lists up. That's why I'm asking. If you need it longer, say something before I start erasing. 1, 1,000, 2, 1,000, 3, 1,000. All right, I'm going to start erasing. So let's see. We're on to example 2 now. My Calc 3 class has a test tomorrow. They are so excited about it. And I go through the grades of the exams. Until I find 10 students that passed. So kind of like my random variable x is is on students that passed. And we want to know, does this meet the 4 criteria? And let's go through the examples. So, fixed number of trials. Do I have a fixed number of trials here? No. I could get the first 10 exams I look at, they could all be passing students. I could have 7 students that failed before I get 10. I could have 15 students that failed before I get 10. So I have to look through more or less than the minimum would be 10 students here, but I could get as high as the entire class if only 10 students passed. So it doesn't pass that one. Does it pass the rest? Independent trials. Does one student's test affect the next student's? Assuming they're not cheating, yes, they are independent. Are there 2 mutually exclusive outcomes? Yeah, they either pass or fail. So that works. And D, probability is the same for all the events. Yeah, whether you consider 70% or higher passing or 60% or higher passing, whatever you're doing, as long as you're consistent on just making that decision for all the tests, that's the same. This is still not a binomial probability because it failed one outcome. Failed at least one test. Or category.
Mr. Jones,
Yeah.
can you go over how you got that again? I'm sorry.
Which part?
How you determine it's not a binomial probability.
Okay, so like if I have the test sorted from high to low, I should get the first 10 tests I look at should all be passing. So the number of tests I had to look at was 10.
Mm-hmm.
If I leave them in alphabetical order, I might have to go through 22 students before I get 10 tests. So the number of tests I look at is considered like the number of trials.
Uh-huh.
And it's not remaining fixed. It's not meeting this rule. I could look at 10 tests. I could look at 20 tests. I could look at 27 tests. So you do not, the main thing that breaks that first one is it never works where you're going till you can't do it until you get so many successes. Or failures, whichever one you're looking at. You can't do that. That's what breaks A.
Okay. Okay, I think I got it. Thank you.
I'm glad you asked. I never know if what I'm saying is clear enough. I just assume it is when no one asks questions. All right, I'll put up another category. I'll give you a couple minutes to think about it. Does anyone need this up longer? I hear nothing. I will start sweeping it and put the categories up. Or put the question up. A pair of fair dice is rolled 10 times. And the number of sevens is recorded. So I'll bring this down so you can see the list again. Try to go through the test here and see if you can figure out whether or not this is true or not. Is this a binomial experiment? That's the word I was looking for earlier, is experiment. Oh, I see a chat thing. Yeah, go ahead, Caprice. Hopefully she can load up her other device pretty quickly while you guys are thinking this out. All right, Caprice is back. Okay, so is there a fixed number of trials?
Yes.
Yes. What is it?
Would it be 10?
Yeah, it's 10. So yes. Are the trials independent? Assuming
I
like
want to say yeah.
yeah. If I throw the dice and then I pick them up and throw them again, there's no reason first throw affects the second throw. Are there two mutually exclusive outcomes?
I was stuck on this one, but I'm going to say no. But is it?
Why?
I don't. Well, I was thinking the no side because like when you roll dice, like can you get 7? Like
Oh yeah, I
looks like
listed the
like a,
sevens right here.
yeah, but
A
like
pair
wouldn't
is
you
2
get like
dice.
3, 4? Like wouldn't you get like other numbers? Like
You can
I
get
doubt
other
we're gonna
numbers,
get
yeah.
7 all the time.
No, you're not going to get 7 all the time. That's why we're recording. If you had 7 every time, then there's only one outcome.
Yeah.
So this is an excellent question. Like, what do we consider? So, like, I could get 6s, I could get 8s. Are we recording those too? In this circumstance, we are only recording whether it's 7 or not a 7. We don't give a shit if it's a 6 or an 8 or a 3 or a 2. We don't care if you get a 12 or 11. It's either 7 or not a 7. Because what I'm doing is I got like a 7 thing and I'm doing a little tally count as I go. Like, how many did I roll? So I'm only looking at the outcome. So this one's
Oh, okay, I
actually a
get you. Yeah.
yes. But it leads to a good question. And that's why I leave this one for that category. I'm always curious to see if someone's going to ask it. Is the probability the same for all the events? There are 6 outcomes that have a sum of 7. There are 30 other outcomes that I did not list here because there's 36 total. So yes, 6 out of 36 successes or wins, and then 30 out of 36 loses. That doesn't change between each roll. So this does pass the binomial probability experiment. This is a binomial experiment.
So where'd you get the 6 out of 36 and the 30 over 36?
So this might be easiest if I'll bring this back up in a second. I'll show you some. So sum of 2 dice. We're going to look at images. There are 36 outcomes here. 7 of them, the diagonal here is 6s. If you add up the other ones, there's 15 above the 7 diagonal and 15 below. So there are 30 numbers here that are not 7s. The way I did it was I know there are 36 outcomes because it's 6 times 6. This was the counting rule thing we did in chapter 5. The number of outcomes, if they're independent, we can just multiply them. This was 5.5 counting rules. So there's 36 outcomes. I know 6 are wins because I listed them out. And so if I know 36 are 6 are wins out of 36, the other 30 must be losses. Another great question.
Okay.
Does that
Okay,
make
thank you.
sense?
Yeah, it does. It does. Yeah,
Okay.
yeah, it makes sense. I remember from chapter 5.
Cool. Let me leave that up a little bit longer, and then we will. Oh, and you know what? Fuck it. I'm going to show you the formula right now because I want to. I kind of want to ruin your day. This is your day ruiner. The probability of x equals n choose x times p to the x times 1 minus p to the n minus x. N is the number of trials. X is the number of successes. And P is the probability of success. And this NCX, that's what we did in chapter 5 at the end. Who's excited to do this by hand?
Just as excited I am. That's for the midterm. Not too excited.
Oh, the midterm is not too bad. It's just hurting my feelings. So this is good news. We're not doing this by hand. So let me write down what we do in StatCrunch. Stats, calculators, binomial. What you need to have to do this, you need N, X, and P. And you just plug them in and it'll do the rest. Well, we'll show you that in a second. This formula is easy to screw up by hand. Okay, you guys ready for more? All right, if you need that back out, let me know. Otherwise, we're going to move on. So let's look at an example. Let's talk about, actually, before I do, I want to make sure I mention inequality symbols. Hopefully you know what all of these mean, because the binomial calculator uses them. If we say x is less than or equal to 3, or this symbol right here, this is less than or equal to. Whereas if we just have x with that like that, 3, this is strictly less than. No equal to part. So when they ask you words like they say less than or equal to, you're in StatCrunch, you choose which symbol to use. So you need to know what the words mean and translate the symbols. If we have where, like this looks a lot like an alligator, I'm going to give him bloody teeth, or a vampire. Like it's going for a meal. And what it means, like the alligator, the vampire goes for the bigger meal. So in these top circumstances, like 0, 1, and 2 is less than, it meets both of them. 0, 1, or 2 for x does either of these. 3 only satisfies the top one. Alternatively, we could have x is greater than or equal to, or let's just greater than. Let's change the number up. 4. Greater than 4. So if there were 10 trials, this one is looking for 5, 6, 7, 8, 9, or 10. If there's a line under it, it's greater than or equal to. So 10 trials, it would be 4, 5, 6, 7, 8, 9, or 10. hopefully that's at least familiar, if not old news for you. But people often get these mixed up. They'll hear greater than and do the top one. It was worth recapping before you start diving into this stuff. And now we can look at an example. Let's do some examples. Does anyone need this up longer? All right. Okay, so for example 1, let's use our finer pins where they show up a little bit better. Make better lines. "35% of car owners have 3 or more cars." We sample 20 homes. To see if they have 3 or more. Cars. And then our questions are, what is the probability that exactly 5 homes have 3 or more? And then we'll take a look at more than 5. That's presumably blue, but that looks kind of purplish on my screen. So in both of these, n is the number of homes we test is 20. The probability of success is given by the 35% will be 0.35. In this problem, x equals 5. In B, it's x is greater than 5. And just to show you how horrible this is by hand, I'm going to write it before we do. Well, I don't need to erase it. If we did this by hand, probability that x equals 5, using that formula we had, would be 20 choose 5. Then we had p to the x, which would be 0.35 to the 5th power. And then we'd have 1 minus p, so 1 minus 0.35 to the n minus x, or 20 minus 5. You could work this out in a calculator, and you're going to get 0.127199185. This is a pain in the butt to do. It's really easy to misfire or mistype something in the calculator. This one's even worse. X is greater than 5 means you got to do probability that x equals 6 or x equals 7 or x equals 8, and you got to do them all the way up to x equals 20. So you got to calculate these individually, one at each time for each x, and then add them all up. Let's do this in StatCrunch. So I'll give you a second to finish writing that, and then I'll load up my math lab in StatCrunch. Okay, I'll start loading that. If you need it back up, let me know. And make this several windows so I can have them up at the same time. So we're gonna go stats, calculators, binomial. What the hell? Oh, I opened up a new one. I guess we're going back into it. I fucked that up somehow. And note, it shows a picture already. It's got a nice bell curve. We are going to change this to say 20 for n. We are going to change that to say 0.35. It's already conveniently set to 5, but this is a changeable field. But we want it equal to 5. So it gives me the probability here. Notice that's what I got written down right here. I got that written down right there, and it shows up right here. Notice also it shows a red line for the what's being looked at. This can be helpful. Like if you're doing this and you get a wrong answer or something like that, look to see if the red lines match what you think they should. If we do the greater than 5, I can do that. And notice now everything greater than 5, but 5 not included, has turned red. And it's giving me the probability here. So this is going to be 0.75460425. And depending on how many decimal places, you'll know if what you need to enter. The reason why I say pay attention to the more than, or the red lines, is like it says more than 5. So like I can see 10 is more than 5, 15 is more than 5. These numbers to the right are more than 5. If I had picked the wrong symbol, I can see these numbers like 0, 1, 2, 3, or 4. Those numbers are not more than 5. I can see I've picked the wrong stuff based on the red lines. So if you pay attention to where the red lines are, it should match what the words are on a problem. So let's add another question here. What about less than 4 homes? And then we'll look at between 3 and 7 homes. I'll say inclusive. We'll talk about what that means in a second. So if I want to do less than 4 homes, by hand it would be probability that x equals 0, 1, 2, or 3. And we'd have to do that calculator for each one. Here, all I got to do is say 4 homes and less than. Between 3 and 7 homes inclusive means I want the numbers between them, 4, 5, and 6, but I also want to include the numbers at the end, the 3 and the 7. So the inclusive means include those end values for between. So binomial calculator has a button at the top that does between. We cannot change this symbol. Notice the symbols are fixed at less than or equal to on both sides. So if I do 3 and 7, it's got 3 highlighted, 4 highlighted, 5, 6, and 7 highlighted. So here I'm getting 0.5889. I'll just write a few at this point. If I said between 4 and 11, and I don't have the words inclusive listed, this is 5, 6, 7, 8, 9, and 10. Oh, I see a question in chat. Yeah, we'll do the SC again. Start from it fresh real quick. We're going to go stats, calculators, binomial. So when we do that, we put in our values. N was 20. P was 0.35. And now I'm going to click on between. And I want between 4 and 11, which means 5 through 10. I can't put 4 through 11 here because, check this out, when I do it, the 4 gets highlighted and so does the 11. And I don't want those. So you got to pay attention when you do the between. You have to choose values that work. I actually need between 5 and 10. That meets between 4 and 11. Not too bad. Just you got to know what the 3 numbers are. You plug them in. They come from the problems. Any questions on those?
So for D, what did you put in between?
I did 3 and 7 because I wanted to actually include the 3 and the 7. If I didn't want to include the 3 and the 7, I would do 4 and 6.
Oh, so inclusive is including?
Inclusive means include the endpoints.
Oh, okay. All right. So like you did 5 and 10 because it's closer to 4 and 11 for E?
I did 5 and 10 because that's the whole numbers between 4 and 11. If you're counting up
Oh, it's the
4 to
whole
11.
numbers. Oh, okay. I was gonna say yeah. Okay.
Right.
Thank you.
There's no like you can't have 4.5 successes. These are all going to be whole
Yeah.
numbers.
Yeah. Okay.
Okay.
Can you do another example of like E with like other numbers?
Sure. Let's say we're gonna change the probability to 0.10. Let's change n to 50. And let's say between 3 and 18. So what we're going to do is I'm going to fill those things in. Three and 18 means I don't want the 3. So I got to pick the next higher number up, which would be 4. And I don't want the 18. I got to pick the next lower number down, which would be 17.
Okay, that was my question. Okay, so the first one's always one number up and the second one's always one number down?
If it doesn't say inclusive, correct.
If it doesn't say inclusive, correct. Okay, yeah, that was my question. Perfect. Okay.
It also leads me to show you, look at how the probability looks here. It's not in the center anymore, is it?
No.
Like if I do 0.1, watch how bad this gets. Maybe I'll change this up to like 1,000. Nope, that's too high. Let's go 100. So 0.1 or 0.1 is like that. 0.10 or 15. Well, that's a little bit more centered. 0.10, still okay. Still a little bit to the left though. 0.5 is definitely to the left. So that's going to bring up something that we want to pay attention to. First off,
Can you go back to that last page real fast?
yeah.
Okay.
So a couple things. If you have a low, and this gets worse when n is low. Let's go back to n equals 10. I did not change that. There you go. 0.05 is terrible. 0.15, still very lopsided, right? This is skewed right. The tail is on the right. 0.25, still skewed right. The value is not in the middle. The hump is not in the middle. What about like 0.35? Starting to get closer. If you have 0.5, it's always going to look perfectly symmetrical. So where I'm going with this is if n is low, a couple things happen. We didn't have the same problem when n was 1,000. I could put in 0.1 and it didn't have any, you could barely see that it's skewed. 0.05, still, you can't really notice it's skewed. When we had n equals 10, you can see it's definitely skewed. So if n is low, different things kind of take the floor. If p is 0.5, which is 50%, it's bell-shaped. As we can see, if I change this to 0.05 or 0.5, it's nice and bell-shaped. If p is low, which is what I just showed, it's skewed right. And if p is high, what do you think will happen if I make p a high number?
Skewed left.
Should be skewed left, right? The other version? Yeah, skewed left. So most of the shit we're doing, we want a bell shape. This is what we want. So if p is too low or too high, we want a larger n, or a larger sample size. And we have a formula for it, and they're going to ask you, or they'll have you use this in problems. We need to pick n such that n times p times 1 minus p is greater than or equal to 10. And you might be going, okay, well, what the hell does that mean? Let's look at an example. If p equals 0.21, what should we use? Now let's change it up. Let's go 0.24. Well, we have n times 0.24 times 1 minus 0.24 is greater than or equal to 10. That 1 minus 0.24 is 0.76. And so you can either multiply first, then divide, or I'm just going to show what it looks like if we just do the straight division. I'm going to divide both sides by that 0.24 and that 0.76. This will show me that, let me put it up here, n needs to be greater than or equal to 10 over 0.26 and 0.24 and 0.76. Well, what is that number? 10 divided by 0.24 divided by 0.76. Where's the decimal point there? 54. This is saying 54.8. So n needs to be 55 or larger. +55. That's how you use that calculator. Notice if we did p equals 0.5, this becomes n times 0.5 times 1 minus 0.5 is greater than or equal to 10. 1 minus 0.5 is the same thing as 0.5. This is n is greater than equal to 10 over 0.5 and 0.5, which is 40. So like even when it's like you kind of want your sample size to be 40 or more. Is ideal. We don't always have that though. So your results may vary. If p is low, you definitely want to pick n so that it meets this. If it's not bell-shaped, we can't use that empirical rule model. You know, the pretty graph with the between 2 deviations, between 3 deviations. We can't do any of that. So where do all these pins come from? Oop, I don't have that capped. There is one more thing I want to show you in 6.2, and then we'll do 6.3, which is a lot shorter. While you're writing that, I'm going to clear some boards. And do you need that up any longer? If you do, let me know. I'll bring it back. That's some calculus 3 shit right there. You think you got it bad. That's not even the worst of that. That actually has mostly numbers and letters. There's a lot of Greek letters in that class. Okay, so I told you we want the empirical rule to be able to work. Empirical rule has standard deviation and mean. So what is the mean and standard deviation for the binomial experiment? Mu of x is n times p. In the problem we did with the houses and the cars, 20 times 0.35 is 7. fact, if I go back to doing this, you'll see that 7 is right where the big tallest number is. It's the tall one. Standard deviation. You're going to do n times p. You're going to multiply it by 1 minus p. And then you're going to take the square root. So in our example with the homes and the cars again, I already did the NP right here. This part is 7 from the mean. 1 minus P is 1 minus 0.35. And then we're taking the square root. So 1 minus 0.35 is 7 times 0.65. Oops, put the decimal in the right spot, David. We take the square root. I recommend doing the stuff inside first, like I'm doing here. And then I'll take the square root. And I'm getting 2.13. If you try to do it all at once, check out what happens. Square root of 7 times 0.65. I'm getting 1.7. I didn't get the same answer. The reason why is that 0.65 is underneath, and the way I put it in the calculator didn't show it. If you have parentheses things, you can use parentheses to do that. And then you'll get... Oh shit, I had 0.7 that time. And if I use parentheses, it's right. But it's easy to forget the parentheses. So I recommend doing the inside first, then doing the square root. And that'll be it for 6.2. You guys ready for 6.3? This is pretty exciting. I know you're excited about it. Don't party too much. Okay. I'm going to start on 6.3. So 6.3 is on the Poisson distribution. It is not Poison, it's Poisson. Just like our binomial distribution required some rules, the Poisson distribution has requirements also.
There was a question in the chat.
It's not showing up on my screen. He asked me if I could do the stack crunch again. I did that a little bit ago.
Okay, sorry.
It's okay. But if you want to see that again, stats, calculators, binomial. You can also see Poisson down here, which is where we're going. So that's handy. Let's take a look at our requirements. The first requirement, the probability of 2 or more successes in a small enough interval Interval is like number range. Is 0. If we make the interval small enough, like if it's time-based, if we get down to small enough time blocks, there's no way it can happen more than twice or more than once. 0 or 1 time. But you might have to make the intervals small. So like an example of this is like 2 cars in a drive-through window in an interval of 6 seconds or in 3 seconds. Sure. In 30 minutes. No. The probability of 2 or more successes is probably greater than 0. Unless it's just a shitty fast food place. So, like, you can make the time fragment or interval small enough. The next thing is the probability of success. Is the same for any 2 intervals of the same length. And finally, what we really always like for everything, the number of successes in one interval is independent of other intervals. What does that mean? The intervals don't overlap. I'm really sad we're not in person for this. I'll show you, you'll see why. And you'll go, God damn, Mr. Jones, you are one sick fuck. You are a sick man. You need help. So while you're writing that down, I'm going to load up my next thing. I had this. I thought I had this in my bookmarks. There we go. Oh, shit, that didn't. Search is bad. You guys ready for the example? So my example, the FDA Food and Drug Administration sets a food defect action level called the FDAL for various substances that inevitably end up in our food and drink. And what this means is like if the substance exceeds a certain amount, specified value, the product is defective and cannot be sold. Which means don't eat it. Okay? So, what is it for chocolate? And I loaded it up on the screen because you need to see that I ain't making this shit up. So I'm going to expand it so you can see it a little bit better. Where'd it go? Insect filth. $60 or more fragments per 100 grams. Ooh, rodent filth is even better. 1 or more rodent hairs is considered defective. So how does this work in Poisson distributions? $60 or more fragments. This is why I'm a sick fuck. I generally start this session by handing out bags of M&Ms, and we count colors and do it to be used for a later experiment. And then and then I tell everybody they can eat their candy after we've counted up the colors. And then after they've eaten their candy, then we start doing this section, and I get to point out how much insect filth they just ate, which is very, very nice of me. So where am I going with this? Okay, so insect, 60 fragments per 100 grams. A fragment is like eggs, wings, larvae, etc. That's insect filth. So 60 fragments per 100 grams. If you do that division, you get 0.6 fragments per gram. So let's take a look at a Hershey bar. A Hershey bar is, you know, good old milk chocolate Hershey bar, 1.55 ounces, which is about 43 grams. So we're going to look up the probability of exactly 3 parts, 3 insect parts, or 3 fragments. Then we're going to look up fewer than 3. And why not greater than 3? In StatCrunch, it's stats, calculators, Poisson. I think there's a French person, Poisson. I like the name. It looks pretty cool. Sounds cool. So let's see what it asks for. It wants the mean. And we need X, what we're aiming for. So how do we find the mean? We didn't actually talk about this yet. The mean is how do I want to say this? I'll use the formulas they do. Mu of x equals lambda times t. Lambda is the rate or average number of occurrences. T is our interval. And x is obviously the number of successes. We did this before with binomial. Interval is often time, but not always. Like in this case, it's not time. While I'm giving you mu of x, I might as well give you sigma of x. The standard deviation, really easy. Square root of lambda t, which is the square root of the mean. I'll give you a chance to process that, and then we'll maybe if we got time, we'll look at a homework problem. How's that sound?
Great.
I thought you might like that. So for our problem, for the Hershey bar, this is our average. So that's my lambda. The interval here is like 1 Hershey bar, so like 43 grams. So T here is the 43. Ideally, if you're doing this correctly, you got 0.6 fragments over 1 gram. Whatever the time interval needs to have the same thing as the bottom. It needs to be in grams. So T has to be in grams. That way, grams cancel. And we're just looking at fragments. So in this case, it's 43 for the Hershey bar. So 0.6 times 43 is 25.8. And we can compute the square or the standard deviation just by taking the square root. 5.079 for our problem. So I'll re-show you how to get to it in StatCrunch. Stats, calculators, Poisson. So we just said the mean was 25.8. And we wanted exactly 3 fragments, so exactly would be equals. Well, this is pretty good. Exactly 3 is pretty low. 0.00, God, how many zeros are there? 1, 2, it looks like 7 zeros. Very low percentage. Fewer than 3 should be even lower. E to the negative 9 means shift the decimal place left 9 times, which means 8 zeros. Greater than 3. A lot of 9s. You are 100% certain to have more than 3 pieces of insect in your Hershey's bar. There's at least 3 pieces of insect filth. Well, 3 isn't very many. Like a little tiny piece of a wing, that may not be that bad. Only 3 of them? That's not too bad. What if it's like 10? Let's look at like 10. What's the probability of more than 10? Oh shit, now that's still not good. It's still almost 100%. 99.96%. What about more than 20? Jesus, it's still 85% likely that a Hershey bar has more than 20 insect fragments in it. What about 30? Well, now it's starting to drop off. 0.1758 is 17.6%, which means about 1 in 5 bars, 1 in 6 bars. 1 in 6 Hershey bars has over 30 pieces of insect filth in it. Isn't that good stuff? Or could have up to that many, I should say. Because if it has that many, when they're doing a count, they say it's defective. So up to that amount. Any questions? If you're ready for more, I'm ready to go on. I thought maybe I better show you the formula just so you know it or have seen it. You are not doing this. So the Poisson distribution. The formula is probability of x equals lambda times t to the x power divided by x factorial times e to the negative lambda t. All of these are available on a calculator, but this is a pain in the ass. So let's go to look at an assignment. We'll look at homework 6. Question 19. The reason why I bring this problem up is people get stuck on it and go, what the hell are they, what's being talked about here? So it says for the past 100, and I'm going to write it in terms for my lecture video. For the past 109 years, a certain state Florida is under threat from a hurricane. Let's just use Florida as an example. Suffered well, Florida is probably a bad example because they get hit with hurricanes more on that. Let's go with, like, I don't know, Virginia. Something higher north where it doesn't always get there. Suffered 24 direct hits from a major hurricane. The category is not important for the thing. The point is it was hit by a major hurricane. Assume this was typical. And notice it says, and the number of hits per year follows a Poisson distribution. Okay, when you get the problem written down, we'll go on and start talking about what we need. I guess I could look to see what the question was. What is the probability that a state will not be hit? In a single year. Okay, assuming you got the problem written down, we need mu, which is the mean. We need mu. And we need x to do this question. Well, recall mu is lambda times t. They give me the time interval. Look at this. In a single year. That's t. I was telling you we need lambda, like this thing needs to be in the bottom of lambda. So lambda needs to have year on bottom. Notice it tells you number of hits per year. Well, that's what lambda is. That's our average. Hits per year is the average. Well, we don't know what the probability is normally, but we do have numbers for the last 109 years. The last 109 years, there were 24 hits in 109 years. So mu of x is going to equal 24 over 109. That's my lambda times t, which was 1. So 24 divided by 109. And I'm going to write down as many decimal places as I can and use as many as I can in the program. There we go. That was blocking my view. And it happens to equal mu because it was times 1. Maybe I should just leave mu right now. So that's what I'm going to put in. I'm going to put in everything my calculator tells me. I'm not going to be lazy and stop at 0.22 because there's a good chance I'll get the wrong answer if I do. So don't be lazy. Put everything the calculator says. It says the probability the state will not be hit in a year. What does that mean x is here? Well, X is recording the number of hits. If it's not hit, X has to equal 0. So I'm getting that the probability that X equals 0 is 0.80237156. How much does this change if I round it to like 0.2? Oh, yeah, it changed a lot. 802 is up to 818. What about 0.22? Well, that's closer. 0.8025. We had 8023. I'm going to put them all back in. Because I don't know how many decimal places they wanted for the answer. 220183486. There we go. Then we go back to my answer, my question. Round to 4 decimal places. 0.8024. If I had rounded to 0.22, I would have got the wrong answer. What is the probability the state will be hit by at least one major hurricane? Well, at least one means one or more. So at least one is greater than or equal to 1. Why do I have a 2 there? What the fuck? There we go. Oh, I got a 0 in there. Look at that. Always check to make sure you didn't typo when you're getting the answer. Then make sure you wrote down the wrong or right thing from MATLAB and that you didn't round too early. Is this unusual? A probability of 0.1976. 1976 means it's happening 19.76% of the time. Unusual is less than 5%, so this is not unusual. What about at least 3 major hurricanes? Means X is greater than or equal to 3. As it says, as happened several years ago. So some state had a bad year. And just set this to be 3. Click compute, and what do we get? 0.00150968. I'm assuming they still want 4, but I'm going to write them all down just in case they try to trick me. Because you know they do. Every once in a while, all of a sudden, it'll be 3. You're like, MF, it was 4 the whole time. Why'd you change to 3? Check answer. Is this unusual? If the probability is less than 5% or 0.05, it's unusual. So in this case, yes, it is less than 5%. And it's starting to get repetitive. At least 2. I gotta come over here and do changes to 2. What? How about we turn off our music? I can't believe you're listening to music and not me. That hurts my feelings. That was a 5, which means I need to round up to a 10. Shame on you, Emmanuel. That's bigger than that's smaller than 0.05, so yes, that's unusual. And that's it for that problem. So that's how you do the hurricane problem. And unless you have questions, that's it for today's lecture.
My bad, Professor Jones was starting to do my homework and didn't realize I pressed on mute.
Right? Doing homework
My
while
bad.
I'm lecturing. Shame on you.
It's because I was getting ahead.
Well, that's a good sell, but you shouldn't do. In general, you don't want to do that during class. You might have missed something, but you didn't. And I
Yeah.
already told you I was at the end. I'm just fucking with you right now.
All right. Have a good one. My bad.
You too.
My bad.
There's no questions. You guys are free to go, as most of you have already. Stop recording.
Recording stopped.
And I'll say end.